Good morning, students. In this class, we will discuss about the shapes of atomic orbitals. So, when plots were drawn between electron wave function or wave functions of orbitals as a function of distance from the nucleus r against the distance. See, I am repeating. When wave functions of orbitals as a function of distance from the nucleus psi r is plotted against the distance, it was noticed that these graphs or plots were observed as different for different orbitals. These plots were observed as different for different orbitals. For example, for a 1s orbital and for a 2s orbital, you can notice the difference. See here, for 1s orbital, the value of wave function psi is very high at zero distance, means at nucleus, and is gradually decreasing with increase in distance from the nucleus and is reaching zero. Means zero nuclear influence distance, that is. Similarly, for a 2s orbital, electron probability is very high and decreases with increase in distance from the nucleus, and after zero also it is approaching as negative probability. As negative probability has no meaning, to avoid the psi square, the square of the wave function psi square was considered, which gives us the maximum probability of finding an electron. That's why psi square was termed as electron probability function. When psi square was plotted against the distance from the nucleus as a function of r, here also they noticed that with increase in distance from the nucleus, the value of psi square, electron probability, is very sharply decreasing and is approaching out of nuclear influence. Similarly, for a 2s orbital also, electron probability was sharply decreasing with increase in distance from the nucleus, and at one point it is approaching zero electron probability, zero electron probability density, and after that again there is an increase in probability density. After reaching a maximum, again it is decreasing and is reaching out of nuclear influence. In this way, the plots of these wave functions of orbitals against the distance from the nucleus were observed as different for different orbitals. And to explain this, Born had considered psi square at a point. Psi square means wave probability function, electron probability function. Psi square at a point, suppose this is the nucleus. Around the nucleus, suppose we are noticing the psi square of an electron. Then psi square at a point gives the probability of finding the electron at that point. Psi square value of an electron at a given point indicates the probability of finding the electron at that given point. Like this, when electron probabilities were plotted around the nucleus, see, this electron dot picture or charge cloud picture gives us a bit clear explanation about the finding an electron. See, so this is how electron plot picture was noticed. And in these plot diagrams, this is for 1s and this is for 2s. In these diagrams, the density of dots in a given region represents the probability of finding electron in that region. More the density of dots, more is the probability of finding an electron. And one more point was noticed here. See, for a 2s orbital, here initially there is a maximum probability density for an electron, and after crossing certain distance, see, this is all space, such a region where there is no electron cloud charge observed. Means that region is such a region where the electron probability is zero. The region where psi square value is zero. Psi square means probability density function. The region where electron probability means the psi square value is zero is said to be nodal region or nodal surface or simply nodes. And it was observed that for a given ns orbital, number of nodal regions can be calculated as n minus 1. It is for only ns orbital. For an ns orbital, nodal regions can be calculated as n minus 1. Means for a 1s orbital, 1 minus 1, 0. See, for a 1s orbital, there is no zero probability region. For a 2s orbital, 2 minus 1, number of nodes or nodal surfaces can be calculated as 2 minus 1. Means this is for a 2s orbital. So, between first probability density region and second probability density region, you can notice a zero probability region. This total region is called as nodal region for 2s. Like that, if you notice for a 3s, this is nucleus, This is nucleus. The first probability region is this one, second probability region is this one, and third probability region is this one. Between first and second probability distances, one nodal region. See, this is empty space, all indicates zero probability of finding an electron. Similarly, between 2s and 3s, another zero probability distance can be noticed. So, this region and other region. See, between 1s and 2s, this region is one nodal region, and this region is also another nodal region. Thus, for a 3s, there are two nodal regions. So, that's what calculated using this relation. 3s has a 3 minus 1, 2 nodal regions. And this electron probability density picture was more clearly studied using boundary surface diagrams. Boundary surface diagrams of constant electron probability density had given a more clear picture than the electron charge density picture. See, this is a boundary surface diagram for an s orbital, for 1s and for 2s suppose. And they had given a clear picture, and it was observed that with respect to these boundary surface diagrams, s orbital, shape of s orbital was noticed as a sphere which was centered with a nucleus. See, boundary surface diagram for an s orbital is actually observed as a sphere centered on a nucleus. Means it is spherically symmetric, means electron probability is equal in all directions along x, y and z axis, right? And for a p orbital, the boundary surface diagrams were observed with two sections called as lobes. These are the two sections observed for a p orbital. And when it comes to the quantum numbers, suppose n is equals to 3, third main energy level, if you observe, it has how many sublevels? 0, 1 and 2. 0 to n minus 1. We studied in the previous section. Number of subshells under a main shell can be calculated as 0 to n minus 1. Designated as 0 to n minus 1. 0, 1 and 2. 3 minus 1, 2. Every subshell has several orientations, namely given with a magnetic quantum number. For L is equals to 0, means S subshell, there is only one orientation, that is called as S orbital. This S orbital shape was observed as spherically symmetric, concentrated on a nucleus at the center, right? Spherically symmetric, and which is having nucleus at the center. See, sphere centered on a nucleus. And for a p sublevel, number of orientations are 3, ranging from minus L to plus L, including 0. So, for a p sublevel, L value is 1, we are aware of that. For this p sublevel, there are 3 orientations, minus 1, 0 and plus 1, which were observed along the 3 axes. One is along x axis, one is along y axis and z axis, which are perpendicular to one another. Thus, shape of p orbital is like a dumbbell, where the electron density is concentrated at this region more. Electron density is concentrated more at these regions in the lobes, corresponding lobes. And when it comes to the 3 p orbitals here, see, this is a px orbital where electron probability is concentrated more along x-axis. See, along x-axis only, not more along x-axis, along x-axis, and along y and z. See, its probability is 0. Thus, you can notice one thing. The plane joining these two x and y axis and is passing through the nucleus. The plane passing through the nucleus with respect to y and z axis, there is no px electrons. See, px electrons are only along x axis, right? So, this yz plane is called as a nodal plane. This yz plane is called as nodal plane. YZ plane is the nodal plane of px electron. For px orbital, YZ plane is said to be nodal plane. The same way, another p orbital, that is py, for which this xz plane passing through the nucleus. XZ plane passing through the nucleus is said to be nodal plane. So, nodal plane is XZ for py. And here for a pz orbital, this plane passing through the nucleus, what is the plane? XY plane passing through the nucleus is called as a nodal plane for a pz orbital. In this way, for a px orbital, one nodal plane; for py orbital, one nodal plane; for pz orbital, one nodal plane. Okay, this is about for a p orbital. And when it comes to the d orbital, under d sublevel, for L is equals to 2, Under D sublevel we have got 5 orientations, minus L to plus L, no? So for the corresponding L is equals to 2, number of orientations are minus 2, minus 1, 0, plus 1 and plus 2. These 5 orientations corresponds to 5 d orbitals which were designated as dxy, dyz, dzx, dx square y square. Of course here hyphen is given, and dz square. We should not pronounce it as minus, okay? It is not a minus frankly. dx square y square and dz square. Here one more point you have to notice. As these are given px, y, z, px corresponds to minus 1, py corresponds, there is no such assignment, okay? See, as 3 orientations are possible, 3 orbitals were named in that way. That's the point we have to remember. There is no convention that for px minus 1 and this one py 0 like that. We can assign any number, any orientation to any orbital, right? The same way, these are the 5 orientations possible for a d sublevel, which are designated as dxy, yz, zx, x square, y square and z square. We need not assign this value for a particular orbital like that. Just 5 orientation values, 5 orbitals. And with respect to this boundary surface diagram, the shape of d orbital was observed as a double dumbbell. Shape of d orbital was observed as double dumbbell like this. For a dxy orbital, see, electron density is between x and y axis at 45 degrees angle. See, this is x axis and this is y axis. Between x and y axis, this is a perpendicular plane. Suppose this z axis is like this, perpendicular to the board. So this assume this z axis as perpendicular to the board in the direction of this plane. Then electron probability for in a dxy is between x and y axis. Similarly, for a dyz axis, assume this pen as x axis, then electron probability is between y and z. Similarly, for a dzx axis, dzx orbital, assume this pen as y axis, then electron probability is between z and x. In this way, the shape of d orbital was observed as double dumbbell, and these are the corresponding shapes. You can notice among these 5 d orbitals, 4 d orbitals are of a similar shape and 5th one is different. Okay, electron density is mainly concentrated along z axis with what's this called as, with some spherical electron density at the center. Right, so thus the shape of 5th d orbital is observed as different, but these 5 are having same energy. Thus orbitals having same energy were called as degenerate orbitals. What are these 5 orbitals called as? Degenerate orbitals. Orbitals having same energy were termed as degenerate orbitals. Similarly, this px, py and pz under a given subshell are also observed as degenerate orbitals. What are degenerate orbitals? Orbitals having same energy, because when you consider this px, py, pz, suppose these 3 orbitals comes under third principal quantum number and one azimuthal quantum number. As 3 and 1 are common for these 3 orbitals, usually energy of orbital depends on their corresponding n and l value. For px, py and pz, as n and l value are same, obviously their energy will be same. Similarly, for dxy, yz, zx, x square minus y square and z square, 5 d orbitals, n and l values are same. That's why these 5 were observed as of a same energy. In this way, the set of these 3 orbitals were called as degenerate p orbitals. These 5 d orbitals were also called as degenerate orbitals, degenerate d orbitals. And when it comes to the nodal plane, for a px orbital, this yz plane acts as a nodal plane, because in this particular plane which is passing to the nucleus, no px electron density can be noticed. Similarly, for a py orbital, this perpendicular plane which passes through the nucleus means zx plane is the nodal plane. For a pz orbital, xy plane acts as a nodal plane. When it comes to dxy, there are 2 such nodal planes. For a dxy, there are 2 such nodal planes where electron probability is 0. They are, for a dxy, yz and zx acts as nodal plane. For a dxy orbital, this yz plane and this zx plane, this zx plane and this yz plane acts as nodal plane. You have to assume 3-dimensionally like this. Thus, these nodal planes were also termed as angular nodes. nodal planes were also termed as angular nodes, which is equal to their azimuthal quantum number. Suppose for this azimuthal quantum number, what is azimuthal quantum number for p orbital? It is 1. So every p orbital has one nodal plane. What is azimuthal quantum number for any d orbital? For any d orbital, azimuthal quantum number value is 2. So its number of nodal planes are 2. Similarly, already we discussed about nodal regions. Suppose for if you consider an s orbital, already we have studied that one. This is for 1s, this is the only region of probability. For 2s, it is first probability region and second probability region. For 3s, first, second and third probability region. For 1s, number of nodal regions are 1 minus 1, 0. For 2s, 2 minus 1, one nodal region is there. This total region where no electron can be noticed is nodal region. It is also called as radial nodes. Radial nodes can be calculated for ns orbitals as n minus 1. For 3s orbital, 3 minus 1, it is 2. See, this is one nodal region and this is another nodal region or radial nodes. See, there are two terminologies with respect to nodes. One is nodal regions, means spherical nodal regions, and other one is angular nodes or nodal planes. Angular nodes or nodal planes can be calculated with the value L for a given orbital. For an s orbital, L value is 0, so 0 nodal plane. For a p orbital, L value is 1, so 1 nodal plane each p orbital has. For a d orbital, L value is 2, so each d orbital has 2 nodal plane or angular nodes. So for an f orbital, L value will be 3. If an f orbital exists, it comes in a fourth, it starts from fourth main energy level. For an f orbital, L value will be 3. So each f orbital has 3 nodal planes in such a way. Thus, by plotting these principal azimuthal magnetic along with the new quantum number given by Uhlenbeck and Gauss-Smith, that is spin quantum number, one can calculate the number of possible orbitals. For example, under first main energy level, only one sub-energy level is possible which has only one orientation. We already named this as S sub-level, which has only one orientation called as S orbital. Similarly, under second main energy level, which has two sub-levels, sub-energy levels, 0 to 2 minus 1, 0 to 2 minus 1, this is S sub-level and this is P sub-level. S sub-level again has only one orientation called as S orbital, whereas P sub-level has three orientations. P sub-level has 3 orientations called as Px, Py, Pz. As I said earlier, there is no such convention that minus 1 always stands for Px. Simply 3 orientations, 3 orbitals we are assigning. Similarly, under third main energy level, which has 3 sub-energy levels from 0 to 3 minus 1, 0 to 3 minus 1, this is called as S sub-level, this was P sub-level and this was named as D sub-level. As usual, S has only one orientation called as S orbital. P has 3 orientation, namely Px, Py and Pz, and D has 5 orientations, namely dxy, dyz, dzx, dx square minus y square and dz square. Again, I am reminding you, there is no such allotment for dxy minus 2 like that magnetic quantum number. There is no such allotment. Conventionally, 5 orientations, 5 d orbitals, that's it. And the same way, f orbitals also for L is equals to 3. Under fourth level, there are 4 sub-energy levels, 0 to 4 minus 1. Each sub-energy level has certain orientations, minus L to plus L. S sub-level has only one orientation. P sub-level has 3 orientations. D sub-level has 5 orientations. Namely, F sub-level has totally 7 orientations. Each orientation represents one atomic orbital. Now, from the spin quantum number, we have noticed that each orbital can be filled with only 2 electrons, one spinning in clockwise direction, other spinning in anti-clockwise direction. So each atomic orbital can be accommodated with only 2 electrons. I am repeating, each atomic orbital can be accommodated with 2 electrons. So S orbital can be accommodated with 2 electrons, in which if one spins in clockwise direction, other has to spin in anti-clockwise direction. In the quantum numbers we already discussed. Conventionally clockwise is given plus half, means 50% probability is for clockwise and other 50% probability is anti-clockwise. The same way means first main energy level has only one orbital which is accommodating 2 electrons. Second main energy level has totally 4 such orbitals, and each orbital can be accommodated with totally 2 electrons only. Each atomic orbital can be accommodated with 2 electrons. 4 atomic orbitals can be accommodated with totally 8 electrons. And when it comes to third main energy level, it has 3 sublevels and these many number of orbitals. Totally how many? 9, 5, 6, 7, 8, 9 atomic orbitals. See, 9 orbitals, 9 orientations. Each orbital can be accommodated with 2 electrons, one spinning in clockwise, other spinning in anti-clockwise. Like which, if you fill the electrons totally, this third shell, third energy level or third shell can be totally accommodated with how many electrons? 18 electrons. 9 orbitals, 9 to 18 electrons. And when it comes to the fourth main shell or fourth main energy level, which has 4 sub-energy levels, under which totally how many atomic orbitals are coming? 7 plus 5, 12 plus 4, 16 atomic orbitals, where each atomic orbital can be accommodated with 2 electrons. Each atomic orbital can be accommodated with 2 electrons. One is plus half, other one is spinning in minus half, right? So if you count those total number of electrons for all these 16 atomic orbitals, totally the fourth main shell can be totally accommodated with the 32 number of electrons. 32 number of electrons. Thus, the number of electrons that can be filled in a given main energy level also can be counted. See, for n is equal to 1, 2 electrons. For n is equals to 2, 8 electrons. Means what? See, one notation we can generate. Under first main energy level, how many orbitals are possible? 1. Under second main energy level, 4 orbitals are possible. Means 2 square. When 1 square here indicates the number of orbitals under 1, 2 square indicates number of orbitals under 2, 3 square indicates number of orbitals under 3, and 4 square indicates number of orbitals under 4. So, we can calculate it as number of orbitals in nth level. Number of orbitals in nth level is n square. Remember these formulas. I am repeating. Number of orbitals in a given nth level can be taken as n square. When each atomic orbital can be accommodated with 2 electrons, n square orbitals can be accommodated with 2 into n square. So, number of electrons in a given nth level, number of electrons in a given nth level can be given as 2n square. So, n square indicates number of orbitals, 2n square indicates number of electrons in a given nth level. N square indicates number of orbitals possible in nth level. 2n square indicates number of electrons possible in nth level. Suppose first main energy level has 2 into 1 square, 2 electrons. Second main energy level has 2 into 2 square, 8 electrons. Third main energy level has 2 into 3 square, 18 electrons. Fourth main energy level has 2 into 4 square, 32 electrons, like that. So once again, n square indicates number of orbitals in nth level, and 2n square indicates number of electrons, maximum number of electrons that can be filled in nth level. Understood?